Okay. Good afternoon. We are now 5 students. My question is, can you hear me?
Yes, we can hear you.
Okay. And can you see the slides on your screen?
Yes, everything okay? Thank you.
Okay. Then let's start with our third lecture. First of all, like in the last lecture, I tried to make a short summary what we have discussed in our last lesson. And we started with thinking about how can we determine radiation pattern of an antenna. And one of, let's say, more or less primitive method is to go over the so-called, radiation intensity U, and together with the power density S. And the product of both, it's independent of the radius, so that we can determine the, let's say, power distribution or the radiation intensity over the surface of a sphere. And at least we looked, this was our example on hand of the Hertzian dipole. What happens if we make a relation to the maximum of the radiation intensity here? And this is only because of the sine function. It's clear if the sine function is 1, then we have the maximum. And if we relate this to the maximum, we have this simple formula. It's only the sine function in square u divided by u max. Okay, and the same problem. Yeah, and if we look to the distribution along the axis and make a cut, this is a special cut here, then we can see here it looks like a 8, and this is the correct radiation pattern if we make a cut in the plane xz. It looks like an 8 here. And if we make a cut through this plane here, this is the xy plane, it's clear then, because the toroid, we have cut it here, has an inner diameter of 0, then we can see only this outer circle. This is visible here. This is a very primitive example regarding how to determine the radiation pattern. Then I gave you some other examples, especially what can we find out with the radiation pattern. This is, let's say, the key point. We want to know which parameters, which special performances or other things we can find from our radiation pattern. And again, we have to consider, you can make, let's say, two main cuts through the 3D, let's say, radiation figure of the antenna, and we say it's the azimuth. This is the plane normally parallel to the surface of our Earth. This is the so-called azimuth plane. And the other plane, it's perpendicular to this plane. This is the elevation plane. Then I showed you some different figures. This is a little bit more complicated, also with the special cuts. Here we have also the cut switchback in, let's say, in the ZY plane. This is visible here, and in the XY plane, this is visible here. This is with the smaller, for instance, half power beam width. This is the opening angle. Half power beam width means 3 dB from the maximum. Then we had a short discussion about the so-called radiation resistance and efficiency. First, I started with the efficiency, small e. It's nothing else in this case as the so-called radiation resistance divided by the sum of the radiation resistance plus the loss resistance. In every case, the antenna, also if the antenna, let's say it's a full metallic construction, we have losses because the conductivity is not infinity, it's limited. We can assume copper, we can assume silver, but nobody will build an antenna with pure silver. But nevertheless, also silver has infinity of, it's not infinite, it's limited to a certain value. Yes, this was a short discussion regarding the input impedance, what we have to fulfill, that our antenna, it's without imaginary part, means the antenna is in resonance, means we have to compensate the imaginary part here from the source impedance and the antenna impedance. If this is given, if both values are impedance conjugate complex, then we have only ohmic parts to handle. Then I gave you an example to determine the radiation resistance of a Hertzian dipole, and at least first we have to determine the radiated power over the equation over the sphere surface, and this is or must be identical with this primitive formula coming from, let's say, ohmic law. Means the current, the mean value of the current in square multiplied by the radiation resistance must be identical with the radiated power, means with this expression here, and both expressions set equal and solved after this radiation resistance, and then we get this result here. And I also give you another result. The quotient is 4 times, but this result comes from another discussion. Means the Hertzian dipole here, it's assumed as 2 very close charges, very close together charges, not as a line element, like a very, very small wire. In this case, it's a, let's say, two charges very close together. It should be much more smaller than a very small wire or very small dipole named Hertzian dipole. In the literature, you can find more or less both values here. Here only I gave an example if the dipole is very long. It means it has a length of lambda, then the quotient is 1, but it's clear this value, it's not result, it's only coming from the formula, but the value itself is not correct because this discussion assumed that the current distribution along the wire, along this Hertzian dipole, it's constant, and this is never given in case of a wavelength long wire. Okay, this we will see later. Then a short discussion about what is a very often used parameter is the EIRP. I also discussed it. It's nothing else than the radiated power related to the gain of the antenna. Means if the given EIRP is, let's say, 100 milliwatt, it's not the power which goes out from your amplifier to the antenna. No, this is the power which is allowed to radiate in the free space. And it means 100 milliwatt means and the antenna has, for instance, a gain of 10, then the applicable power it's only 10 milliwatt because the antenna gains this power again by the factor of 10, and so it radiates in a certain direction in the free space 100 milliwatt. This is all what you can see here. It's the product of the transmit power and the gain of the antenna, and this is the given EIRP, but it's not allowed to go over to overdrive. Then some other examples of pattern, and then the discussion of what is a reciprocal antenna or what is reciprocity, and I showed or tried to explain it on one of these two antennas. Let's say two equal antennas located maybe not directly perpendicular or not directly parallel in a special way, but this localization you have to hold constant in the room, in the space, and then you only can exchange the voltage, let's say the generator of the antenna A against the current measurement system of the antenna B. You can exchange it here, and then you have to see that in both cases if we apply the same voltage here, we measure the same current. This is reciprocity. Yeah, and we more or less the end of our discussion was the Friis formula, means antennas in free space. We have two antennas, let's say point A, distance small r, point B, the distance between both antennas are again small r. One acts as a receive antenna and the other antenna as a transmit antenna. And if you look to the quotient of the receive power to the transmit power, and this shows us, let's say, the path loss between these two antennas, and the path loss is determined, it's clear, by the product of the gain of both antennas. It's logic, if the gain is very small, the path loss is higher, and if the gain is very high, the path loss is lower. Also given by the distance r, at least it's let's say the radius of this imagined sphere around the antenna, and then you can determine very simple the path loss between these two, let's say, transmit and receiving points. Yeah, then we come at least to the so-called polarization. I try to explain you that the polarization is nothing else than looking to the let's say swinging or pendling plane of the E field of the antenna. You know, if the dipole, for instance, the Hertzian dipole is located along the Z-axis, then the E field, it's also laying in this plane where the Z-axis it's laying in, means the electrical, the end point of the E field vector, it's swinging only in this plane. And if you look in more detail to this behavior of an antenna, of a wire antenna, all these things are valid if you assume that, for instance, the wire has a diameter of very small, means goes against zero. And in practice, this is not given. In practice, the diameter of a wire antenna is not zero. It has a certain diameter. And that means we have also components of the E field not only laying in this case, for instance, Z plane or in another plane, depends on the situation of the antenna in the free space. And so we have also components perpendicular to this direction of what is normally given by the formulas. And this so-called polarization vector, it's determined, or it's given here. Here you have the magnitude of the E field, and then in brackets we have the two components in the theta direction. What is, if I would switch back to our coordinate system with the Hertzian dipole along the Z-axis, you know, the electrical field component, it's in principle only in this plane of the theta direction. But here we have assumed we can also look what happens in the phi direction. And so we can write it in such a way. This is the magnitude of the E field multiplied by this P polarization vector, which contains both components perpendicular to each other. This is the, let's say, the normal vector in the theta direction. This is the normal vector in the phi direction. And so it's clear we can say for a so-called right-hand circular polarization, we must have E field components in both directions with the same magnitude. And it's clear the magnitude, the complete magnitude of the electric component, of the E field component, if this is 1 or set to 1, then the perpendicular components, which are perpendicular to each other in the theta direction and in the phi direction, can be only is the normal vector in both directions, theta and phi, square root of 2. It's clear because the sum, if you square it in both, square root of the square sum of both must be 1, and this is nothing else as regarding the magnitude as what you can see here. And to say what is left, what is right-handed, this is a question of, let's say, definition or international conferences in the past. This we can, for us, determine what we want, but in international scripts and documents, this is given in this way, for instance. Then this is another sketch to understand it, let's say, a little bit better. We assume that our electrical part of the electromagnetic wave, means the E field part, it's going out here, in this case, along in the plane of the x-axis. The z-axis here is the direction of motion. And then we know that our H field component is perpendicular to this one, means in the y-axis or in the y-axis plane. This is shown here. And if you make a snapshot, let's say in a certain point along the z-axis, we can say at this moment this is our wavefront to the time here. And the distance between the maximum is determined by the wavelengths. This should also be clear. And it's also shown here, it's a snapshot of the plane wave propagating through the free space. And here you can see again, we can write again the E field component in such a way. It's comparable with that on this slide here, but it's not written as a polarization vector, but it contains in principle also the components between this direction and the perpendicular direction where the H field is located. And the same you can write also for the H field, and you can see this in the same way. Or in other words, if you look to this propagation sketch, you can see looking to the E field, looking to the H field, both field components have components, perpendicular components, and let's say in the other room. It's not so that only in this plane we have pure E field components, and in this direction of the H field we have pure and only H field components. No, we have small components in the same direction. Means in the H field we have E field components, and in the E field we have H field components. That's all what is to explain. Then again, back to the polarization. If we have pure equal components in this direction, in the x direction or in the y direction, okay, then we have pure linear polarization. It's clear, but in practice it's not given. Again, all the wires have a limited diameter, or in other words, the diameter of the wires, for instance, it's not 0, means it has a special value, depends on other points of view, and so we have, because of that, field components perpendicular to the wished direction. And here we have again this what we what is, for instance, written here on the hand of this polarization vector here, right-handed and left-handed. And this is what I want to explain. Then you have here the components of y and x. In practice, in principle, we have, or it's very, very complicated to excite an exact right-hand or left-handed polarization. It's very, in principle, it's not possible. And so the so-called elliptical polarization, this is the ellipse laying in the free space. Yeah, it's, let's say, the normal case. This ellipse, it's also, it's not only valid if we look to the circular polarization, we will also find an ellipse, but with a very large axial ratio. I give this expression now again, with a very large axial ratio in case of our assumed or wished linear polarization. Means the ellipse it's very small. For instance, what is my pointer? It's very small in this direction here, and very long in this direction. It's very small. This is linear polarization with a very high axial ratio. Means the major axis divided by the minor axis has a very large value. And if we want to go to circular polarization, then the ellipse looks more or less like this figure here. Then we have a relation between the major and the minor axis, this is our wish, which is going in the near of 1. 1, it's the perfect circular polarization. Both axes have the same length. This is the perfect case, but in practice, it's very difficult to achieve this perfect case. Means, in principle, we have elliptical polarization, or in other words, in case for linear polarization, the axial ratio is very, very large, and in case of circular polarization, the axial ratio goes in the near of 1. And this is given here in this formula, and it's not yet necessary now to discuss all the single components. In practice, if you make, for instance, measurements, you can only determine the so-called axial ratio on hand of this measurement values. For instance, this minor axis and here the major axis, and only the quotient is exactly this value. Okay, here I have tried to explain you what happens if we look to two crossed dipoles. Let's say we have one dipole here along this y-axis, and the other dipole is located here in this plane. And now both dipoles are fed with a voltage, a sinusoidal voltage given here, and this is the voltage, let's say, what we apply valid for this dipole in this plane, in the x plane, and here the voltage A is the voltage for a dipole in the y-plane. Yeah, what happens? What is at least the outgoing polarization or the outgoing wave in the cross-section? We can start here with, this is the time axis along. We can start here with the time point 1. It's clear we have to look to both voltages. Yeah, here we have the zero crossing, and here also it's clear we start from 0. And now the next time point 2, we have a higher magnitude. Here time point 2, the same higher magnitude. It's clear this is the time point 2 on this axis. And if we proceed to the maximum, time point 4, 4, and here also the maximum, we go to this point, then we can see what happens. Our combined E field, it's moving from 0 to this maximum. And if we proceed with the time function, with the sinusoidal time function, then we can see it goes back to the next 0. This is 0.7 here. And then the last half wave, it goes again to a maximum. This is the point 11. I can't 11 or 10 or 11. 10 is the maximum, and then it goes back to 0. This is the case if we have two dipoles arranged perpendicular to each other. One dipole in this x direction, and the other it's in the y direction. Sorry. And if we apply the same voltage at the feed points of both dipoles in this way, same magnitude, no phase shift between, phase shift is 0, then the antenna radiates this, let's say, linear polarization, and the E field vector, it's swinging, pendling in this plane here, in this direction, not exactly in the elevation or in the azimuthal direction. It's 45-degree plane. What can we do to turn it in this direction or in this direction? It's very similar. We can only adjust, for instance, the magnitude of this voltage. Imagine I make this voltage 0, then we have only this plane here. It's only one dipole driven by this plane. But in the same way, if we want to keep constant the magnitude, then we have to, in this way, if you reduce this magnitude, we have to increase this magnitude. Also because of the same power, by square root of 2 multiplied this with the magnitude. This is the maximum, and all values that between are changing this angle from 45 degree, let's say, to 0 degree. Yeah, and if we want to drive it to the y direction, then the voltage here also must be 0, and this magnitude we have to increase of square root of 2 multiplied by this magnitude. Then we have exactly this direction of linear polarization. Means in case of linear polarization, both voltages has a phase difference of 0 degree. Turning around here, the plane of polarization or axis of polarization, linear, we can only do it with changing the magnitude of this both voltages. One voltage, it's changing the magnitude in such a way, if it's here, for instance, larger, the other component has to be lower. Now we go in this part of the sketch, and here, in every case, we use the same magnitude. There's no change in magnitude. But what is changed here is the phase angle between the two voltages. We have the same arrangement of dipoles, one in the y direction, the other dipole here in the x direction, like here. Both dipoles are driven with the same voltage, the same magnitude, but now we change the phase angle between the voltages. Yeah, and then we can see here, let's start, for instance, at time 0 with this voltage. We are here. The other voltage has at time 0 a negative magnitude. And so we start, our starting point is here with the outgoing E field component. And now we proceed, we go here to the point 2, mass laying on this axis. We also go to the point 2. You can see we start here, it goes here, point 3, 4, 5, and so on. 7 is this one. 7 is this one. We are here. Point 8, we are crossing the x-axis. Look here, point 8. It's the crossing point in this direction, in the y direction. Yeah, it's okay. And here, point 8 has this value. And so we can construct the ellipse, which is our, let's say, outgoing circular or elliptical polarization. We can construct this in this very primitive or simple way. If we want to have exactly circular polarization in this direction or in another one, then we have to ensure that the phase difference between both voltages, again, the same magnitude, must be 90 degrees. Yeah, if we make the offset of exactly 90 degrees, then you can see here a perfect circle. Okay, this is only for self-study how to design or how to determine the phase angle between the two voltages if we want to, let's say, realize a special elliptical polarization. Yeah, this is also visible here. We can discuss this, let's say, more or less complicate. We can divide the field components, let's say, realizing this elliptical polarization here. We can divide this in sub parts of the field, and then we can construct, let's say, the ellipse. The starting point is what we want to have, at least the circular polarization. Here, this is the full circle, and the radius of this circle is not the sum of the different components. It's the sum of both components, right? For instance, here we have the component of the left part of polarization, and here the small one of the right part. And you can see then here you make the difference, and here you make the sum. Then if the polarization consists of these two different components or parts, then you can construct it in this way. You will find it also in the literature. And what is very interesting, this is the so-called tilt angle means what determines how the ellipse is laying in the free space. What I have constructed in this picture, for instance, this there is, let's say, a tilt angle of, in every case, 45 degrees. The ellipse is laying in this way. You can make the ellipse larger, and then jumps back in this direction, also the so-called tilt angle would be also, let's say, 135 degree, means 90 degree plus 45 degree. But here, or in practice, the ellipse can be localized in the free space with very different so-called tilt angle. The tilt angle has nothing to do with the polarization itself. It has only to do how the starting points of the, let's say, E-field components giving the right or the left polarization direction, how they are located or started regarding this rotation here. Also, you can here see the sum of these components for the left and the right-handed part, and it's clear it must be divided by square root of 2, because the sum of both in square must be or must give the length of the power, let's say, the radiated power part of 1. This is another example of circular polarization, but under a complete other aspect. Let's assume we have here 2 pairs of very small dipoles. I will not say Hertzian dipoles, let's say small dipoles. This is one pair, and this also is one pair. Okay, let's start with the x-axis. This means we have a dipole which a more or less constant current along the dipole or current distribution should be more or less constant. Here it's named I1, and the opposite dipole which builds this pair is the dipole 3. And the general assumption is distance from our origin should be A1 and this A3. And for the second pair on the y-axis, we have the dipole 2 with a constant current I2, and the opposite is the dipole 4 with the constant current I4. Here you can see again what you have, what I have discussed all the time. The wave impedance means impedance of the free space Z0. It's the same here in eta, given in a lot of other textbooks. It's only for remembering. If you find here in the formula the eta, it's the same letter or it's the same value. It means it's the wave impedance here. Okay. For me it was more convenient to use this one. Otherwise, I had to change in all the formulas this value to Z0, for instance. Yeah, and now we can write down the complete not electromagnetic, electric field components. We know it from the Hertzian dipole principle, the expressions, the J key wave impedance. Here in the Euler expression, this part of the field radiating in the free space, and then here we have the product of the current along the dipole and its length. Again, the length is much smaller than the wavelength. Otherwise, we cannot assume that the current distribution along this length it's more or less constant. Yeah, and the angles are determine the observation angles of the electric field components in theta and phi direction. And it's written in such a way here, the field components of the dipole, for instance here dipole 1, and the opposite dipole 3. The question arises why there's a minus, because both dipoles are excited in opposite. That means we have here between these two dipoles a phase difference of our, let's say, a symmetrical feed line of 180 degree. Yeah, both dipoles are fed coming from a symmetrical feed line with a sinusoidal voltage, and so the phase difference, it's 180 degree, means here minus, has nothing to do with this minus here. Yeah, and the other one, the other pair, this is shown here. This is the first pair. It's the second pair. The second pair, the few components are visible here. Product of dipole length and the current, constant current. The components we know already. Okay, what I have again, this is the normal vector in y direction and the normal vector in x direction here. And not normal vector, normal vector of the electromagnetic potential, electrical potential, this and this. So for finite radiated field on the axis, we must have, with these conditions, we can say A1, it's equal A3. A3 means we have here the same distance. We will see that makes the formula more simple. And then with these conditions here, means this is equal this and this equal this. We can write it in to complete E field in this way. So you can see it will be much easier. Yeah, and here in the main bracket, we can see the products. The products are identical, and we can write it only in this very similar way. And also the angles between the products of the currents, and this is the product difference, like here, this part, and this in this part, it's in every case P, means 180 degree. It's only the difference, it has nothing to do with the components between this line and this line. And this is then, it's given later. Now we can write it, this expression, in this way. It's clear we only have then only this products and only the same angle difference. And now we can say all distances are equal, it's identical with A, and then we can, let's say, make a deviation for the condition of circular polarization. This current on the dipoles also identical. Then, and this is the angle between this difference and this difference, must be plus or minus half P. We remember this is the condition for circular polarization. If it's plus or minus, determines the direction of rotation, either counterclockwise or clockwise. And this is shown here again. If we assume angle of the current 1, this dipole here is assumed 0, then the current of, it's the pair, or it means the pair, the angle of the current 2, perpendicular to this one, this is 1, this is 2, and this is written here must be plus or minus half P. The same it's valid between the current, the angle of 3 and of 4. Means the angle of the current, because of excitation, this dipoles coming from a, let's say, differential or symmetrical feed line, it's P of 180 degree, and this is the same, but the angle of the current difference between this pair and this pair. This angle has nothing to do with the angle between the axes. It's the angle between the currents. This must be either a half P plus or minus, or 3 half P plus or minus. And this determines again if the outgoing electromagnetic polarization it's rotating to the left or to the right direction, or clockwise or counterclockwise. Now this it's, let's say, the final result of this discussion. What is shown here? Here, this angular range starting in the middle of 0, this is theta direction. Remember the theta direction, it's the plane in the, let's say, the z-axis. Let's switch back. In our case, let's assume it's the angle, the plane of the y-axis here, because the arrangement of the dipoles are this way. So what we can see here, the distance between the dipoles, here it was determined by the distance, for instance, R. Here we have set it, not R, I mean A. A1 equal A2, A3, A4, identical A. And in the figure, what is shown here, this D, it's equal in principle to A, to small a. Yeah, this is the difference. It's difference between this small dipole here. And it's very low. Yeah, the distance here, it's in the figures, the small d. Okay, let's start. The distance between the dipoles given in wavelengths, this distance, it's 0.2 lambda. And if we have this distance between the two pairs, the pairs of dipoles has the same distance, it's clear, it's only perpendicular to each other. Then we find out that our so-called axial ratio means we want to achieve a perfect circular polarization, and the axial ratio in dB should be, in perfect case, 0 in log scale, because in linear scale, the axial ratio is 1, major axis divided by minor axis, it's 1, and the logarithm, it's 0. Also 10 times 0, it's 0. Okay, this is the perfect case exactly in the middle of, let's say, of our radiation diagram, means we look straight to the radiation direction. And now we go in the other direction, you know, half power beamwidth, we go to the left or to the right, the main direction of the line of sight, and then we can find that our axial ratio decreases. So 3 dB means the axial ratio is 2, major axis and minor axis in the relation of 1 to 2. And this is given here by this green threshold line, 3 dB. And so we can say that we have, if the arrangement or the distance of the two dipole pairs, it's 0.2 lambda, then we have about, let's say, plus minus 50 degree as a threshold, or totally 100 degree opening angle. I cannot say here half power beamwidth, because it's not true. And we can say that our circular polarization degrades from a perfect circle to an ellipse with an axial ratio of 2 or 3 dB, we can achieve this in this angle range of radiation. It's about 100 degree. I mean, so it's very good, but it's a value that maybe can be increased. Yeah, then let's look in a second. Here, the distance between the elemental dipoles, it's 0.3 wavelengths. This is the blue curve now. The red, the black curve, it's let's say the standard case. And here we can see we can make this angle larger. Then we have here minus 60 and plus 60 degree, means totally 120 degree. Over this angle, we can ensure that our axial ratio is minimum 3 dB or better. Now we make the distance a little bit larger now between the dipoles. It's now 0.4 lambda, and this is very interesting. And so we can see that we came in the near of 80 degree plus minus. Let's say it's 75 or so, the total opening angle to hold a circular polarization equal or better 3 dB. It's now, let's say, 150 degree. It's very good. And here we can see the maximum what we can achieve. And this is interesting. If the distance between the elemental dipoles, very small dipoles, it's, yeah, this is, let's say, a figure of merit, 0.443 lambda. This is a value, yeah, you should keep it in your mind. This value allows us to extend this angle of ensuring the axial ratio minimum 3 dB or better in an angle range larger 160 degree. It's, if you look here, it's a little bit more than 80 degree in both directions. Means totally, let's say, 170 degree. Yeah, if we make the distance between the dipoles larger, then you can see that we, yeah, cannot ensure a value better or, yeah, better than 3 dB of the axial ratio. Then this shrinks again our angle range of radiation holding this value. And here, if we make it, for instance, 0.46 lambda, we also shrink it very, very drastically. I mean, this value, it's the optimum value of the distance of the dipoles excited in with opposite voltage, means coming from a symmetrical line. And this value, this is a very sensitive value. You see, if we make it a little bit larger, then the difference between these two values are very, very small. And it's very sensitive in this range, this distance of dipoles. Okay, here between 0.2, 0.3, 0.4, yeah, in this area, the sensitivity, it's not so large. But if you come in near of this value here, you must be very carefully with the, let's say, arrangement of the dipoles. Yeah, this is very interesting. Means if you want to realize an antenna which makes, let's say, a very good circular polarization, depends of the opening angle, then let's say this is one measure to ensure this very large opening angle of, let's say, more than 160 degree for circular polarization with an axial ratio 3 dB or better. This we have to keep in mind. Okay, this was another mathematical perspective of determine the so-called polarization state of an antenna, but this is not so important for our further discussion. Now we can proceed with the radiation pattern of different dipole structures. We have only discussed, let's say, the pattern of coming from the mathematical platform, only discussed the Hertzian dipole. And in principle, we know this formula here. This it's another view, another perspective. In case of Hertzian dipole, we assumed that the current distribution along the wire, because the wire it's very, very short against the wavelengths, it's we can assume it's constant. And now we can see here this current distribution along the z-axis when our dipole is, let's say, localized in our coordinate system along the z-axis. Then we have to consider if the dipole is much longer or it's changing the near of wavelengths, then we have to consider this new current distribution. This is the magnitude at the origin, and along outgoing from the origin, then we will see what happens. This is again the current at the feed point, means origin, and assuming that the dipole is aligned with the z-axis and centered on the origin. This is what I have already mentioned. Yeah. In case of a very, very small dipole, again, the length should be 1% of the wavelengths. In the literature, it's assumed triangular current distribution. The question is why? The dipole cannot have a flowing current at the end of its length. This is only, let's say, a relative given length of its, let's say, of its dimension itself. The scaling. Then the current distribution at the end of this wire cannot be a certain value, it must be zero. Again, the length of the dipole here, it's not going against zero. It has a 1%, a length of 1% of the wavelengths. Okay. And now here in the next case, we assume that the length of the dipole is a half wavelength. And you can see here also, this means that the points are going inside, that at the beginning, starting point of a dipole, then the current must be zero. And this is shown here. If we go with the magnitude of the current, this is shown here on the y-axis. If we go, let's say, in the other direction, then the phase must be changed in this way. Then we can complete it in this way. But we only look to, let's say, the positive values. And here, this is a half wavelength, and here, this is in principle what I have told or mentioned. If the length of the dipole is one wavelength, then we have, because of the current distribution, these two parts. One part is a half wavelength dipole, starts at the beginning, makes in the middle, and then the other value. And now it's twice the length, then we have twice these values. And if it's 1.5 wavelength longs, then we have the same relation regarding the length. Again, this is only the magnitude of the current what we have seen. It's not, let's say, a vector It's without phase. Yeah, this is written here, the dipole current distribution for various lengths. The y-axis is the current normalized to the feed point current, E0. And the current distributions above here can be used to calculate our corresponding dipole radiation patterns by summing up the small field contributions. And this is what I want to explain. The small field contributions in theta direction, in R direction, and the TH in phi direction from a series of Hertzian dipoles of the length dl. This is the basic idea. We have a series of Hertzian dipoles of length dl, and integration depends on the figure of this antennas, in our case, more or less long dipoles. This integration alone makes at least, or we can determine at least the radiation pattern. So this is one method. It is clear we have now not only the dependence of, let's say, the angles of radiation, we also have to consider now the current distribution along the dipole. In case of the Hertzian dipole, we only look to the radiation angles, and because we could assume that the dipole has a constant current distribution, but this is not given here in our cases. And so we can say the E-field component in theta direction, we know this formula already. It's given in this way. And this is the same for the H-field component perpendicular to theta. It's dH phi. We also know already this formula. And now the components in the radius direction, in the radiation direction, because of this very high value of R in cubic, you know, it's assumed, or we can assume it to 0 here, all these 3 components in this direction, DER 0, the same for the H direction in radius, and all this for the theta direction. Yeah, and now the total E field can be written in this way. Again, we know this part of the formula, but what is new is this part. This determines or considers this part the current distribution along our dipole. And now the result of these calculations is shown here. Here this we know already, and now this here considers in the brackets, in the rectangular brackets, this considers now our current distribution. Again here written, you know, the relation between the theta of the E field and the H of the phi, of the phi direction of H. This quotient is again the wave impedance, 120 p ohm. Don't forget it, it's very important. And this is also the magnitude between the E and H field component. It's the wave impedance again. Yeah, the above analysis of the dipole leads to one general means of analyzing antennas. We can say first we have to determine the current distribution, and if we know this, then these contributions of these infinitesimal elements, we can integrate it, or we can integrate it, and then we can find the radiation pattern. Yeah, and this is for the examples I have shown. regarding the current distribution along the dipole, we can look at the radiation diagrams. This is the cut in in this toroid plane, not in this direction, in the, let's say, Z, for instance, Z Y or Z X plane. If the dipole is directed here in the Z direction. We have here in this case, it's analog to the Hertzian dipole. This dipole is a little bit larger. It's clear 1% of the wavelengths. And then we have a gain of about 1.8 dBi. The I, you remember the I came from isotropic radiator. So this is, it looks very similar to the Hertzian dipole diagram. Okay. Now we make the dipole longer, a half wavelength. This is the, let's say, the first resonant dipole, a half wavelength. We know that we have at the end no current, because at the end of a half wavelength long dipole, there's no current flow possible. And in the middle of the dipole, we have the maximum of the current if it's excited with a sinusoidal generator, voltage generators signal source, pure sinusoidal. Then we can say here that the pattern, the gain must come from certain effects, circumstances. So we can see that if we make the same cut like here, then this, the height here, it's a little bit more flat, and means it must be, and if this figure is smaller, means the power is more concentrated in this direction here, these both directions, and so the gain must be a little bit higher than in this case. And you can see here, this is the case of a half wavelength dipole, 2.15 dBi. We can keep this in mind. It's the gain of a dipole. Again, you can use such a dipole as a gain equivalent or gain normal. You can realize exact half wavelength long dipole given at a certain frequency or wavelength, it's clear. Then you know this antenna delivers, regarding an isotropic radiator, delivers us a gain of 2.15 dBi, or the half power beam width means this angle. If this is 0 dB, we go in minus 3 dB, and we cut here these 2 points, and this angle between these 2 points of half power beam width, it's or should be totally 78 degrees. And this is our radiation, not resistance, radiation impedance, or impedance of the feed point of the dipole. The real part, it's about 73 ohms, and this is here a reactive part. And if it's if the dipole is normally in resonance, you can try to achieve it with commentating this reactive part. Then we have only this about 73 ohms or 75 ohms. Now we make the dipole a little bit longer. We make it 1 wavelength long. This is shown here. Means this, the height of this toroid, it's, if you look from the top side, it's again a circle. And this height of the toroid in the cut here, it's much smaller. Means the gain must be higher because all the half power beam width is smaller. And here you can see half power beam width is 47 degrees. Gain, it's not given here, but it's larger than 2.15. Maybe it's 2.78 or so, I don't know. And here, if we exceed the length of the dipole more than a wavelength. And this is very interesting. This is the example of 1.5 wavelengths length dipole. Then we have suddenly a so-called multi-lobe behavior. We have not only these two edge-like figure, these two circles, there's a cut through toroid. Now we have four, and here two small lobes in this diagram. Again, if we want to have, let's say, a gain equivalent or a gain normal, we can use the half wavelength long dipole, and then we can assume these values. It's very simple to realize, and yeah, we can achieve very good measurement results with this dipole as a gain normal or gain equivalent. If we make the dipole longer, one wavelength, then it's a little bit more critical with feeding and so on, and we cannot or we must be very carefully changing the frequency. And if the length of the dipole exceeds the half, the lambda, then we have a multi-lobe behavior of the pattern. And maybe in a lot of cases, it's, let's say, interesting to realize here, for instance, several zeros in the pattern, for instance, to suppress distortions coming from outside. Then it's, for instance, one measure or one thing what we can realize to suppress in the outer space or from the outer space incoming distortions to our receiving system. It's only, let's say, an auxiliary remark to understand why in some cases we make a dipole longer than a half wavelength. This chapter here, antenna temperature, I jump over this now because we want to discuss this at the end of the lecture when we look at the noise behavior of receiver systems and also the contribution of noise by the antenna itself. It should be clear, an antenna is a, let's say, a pure passive element. This is our discussion all the time. It's pure passive, but later on we will see there are also there are realizations of antennas which are built with electronic components, not only pure, let's say, passive elements, wires, and such things. We also can see that, for instance, for transmit and receive purposes, the antenna are combined with active elements, means, for instance, or in the simplest case, with a transistor, power transistors, low noise transistors for receiving systems. And that we have, for instance, a so-called power combining, not realized with wire elements. We speak about a spatial power combining, means the power is combined in the radiated field. It's not done in the plane of schematic, in the plane of connecting single antenna elements. Then the power combining is realized by the superposition of the radiated power. Okay, and we can apply this in case of transmit. We can apply such mechanism, radiating or radiation mechanism. You can apply this also for receiving purposes. And so we have, let's say, N elements with electronic parts with low noise transistors, for instance. And so we also have noise contributions. And also we have noise, and this is visible here. Noise not coming from the environment temperature of the antenna, and heats up the antenna itself, it also comes from the space, from outside, from the sky. We also can receive a certain noise. Yeah, this is discussed here in this part of the lesson, but now let's come to this part. At the beginning of the lesson, I already discussed, or I had already mentioned what happens, or what is the need, the necessity of antennas in case of aerial vehicles. And here we have, let's say, a more or less figure which radio services and which antenna systems and which frequency range we have to count in case of a normal civilian aeroplane. Yeah, and here you can see a lot of very, very different radio services localized at very, very different frequencies. And this is all necessary, or it's a need for the companies which have aeroplanes in their service, and means we have here, for instance, the need to have a weather radar antenna in the nose of this civilian aircraft. Then we have the need of a so-called radio service which determines or observes the so-called glide slope in this frequency range, 329 to 335 megahertz. It's named in our case, it's ultra high frequency UHF. Then we have this traffic. No, this is a TCAS. I worked in this field. We have here two different frequencies, 1030 and 1090 megahertz, and this is for identifying of the aircraft, but this is for the aircraft has to receive this frequency. The arrow goes to this one. Then it's clear we have the GPS antennas and GPS receivers on board, which is, let's say, necessary for determining the position in the air. It's for self positioning of the aircraft. Then we have other services here. The same. It's traffic control. It's also on the top. Then we have here in the VHF range. This is for voice transmission. Then this is here a frequency range regarding the radio altimeter. It's 4.2 up to 4.4 gigahertz. Determines the flight height. The weather radar frequency is given here. It's in the near of X-band. It's 9.375 gigahertz. All these frequencies are fixed for all civilian aircraft, more or less worldwide, which are coming from airport 1 to airport 2, international air traffic. Has nothing to do with, let's say, special aeroplanes only for, let's say, special purposes, for sports, or for military purposes, or for farmer purposes. These are aircraft which has not the need to carry all these things here, like weather radar or radio altimeter and such things, because they can fly it after, let's say, looking with the eyes to what happens under the airplane. For instance, if we go on a large farmer's field. Yeah, the aerial vehicles are fitted with a large number of antennas for transmit and receive purposes at different frequencies, starting at very low frequencies to the very high frequency SHF band. This is for communication, radio, navigation, and radar. You can see here on this image, you see here antennas for satcom communication and also for satellite reception. Yeah, and this is very interesting, and it shows that we have here a high variety of frequencies, and for instance also for let's say ground localized direction finding, we have here frequency ranges from 190 to 1750 kilohertz. That means we have wavelengths of about from in the near of kilometers to 300 or 150 meters. In this range we are working also, and yeah, you can imagine if you want to use a half wavelength dipole for the highest frequency here, then means we need a wire from the cabin here to the empennage along the aircraft from, let's say, 75 meters or about 100 meters. And yeah, this is a problem, not only because it's not so easy to to use such a wire from the cabin here where the pilots are working to this empennage, because also of a certain effects around this, what the antenna should withstand. Then this is only as an overview written here. The aircraft antennas have to withstand severe static and dynamic stresses. It should be clear. Then a normal civilian aircraft, it's flying with a speed between 600 up to in the near of, let's say, 900 kilometers per hour. This is a very high speed against two propeller aircraft in the past 50 years ago. And then we have antennas for high-speed aircraft, means also military aircraft which are flies with Mach 2, means more than 2,300 kilometers per hour. And then we have, it's clear, a very high stress against the antennas on one side, and on the other side we have aerodynamic limitations, and it's not allowed to make the, let's say, that the antenna degrades the aircraft's flight characteristic. This is not allowed. And on the other side, it's the high airstream along the airframe can destroy, if the antenna is not designed correctly, can destroy the antenna itself. Means again, size and shape of the airframe at least determines also the impedance and the radiation pattern characteristics of our antenna, which is necessary for the radio communications itself. This also determines the behavior of the radio service antennas itself. Then the type of the antenna used in a given application depends also, this is another aspect, of the size of the airframe relative to the wavelengths. And this is very important. If we discuss about the antennas, we also have to keep in mind that all dimensions, not only interesting given in millimeters or meters, it's of interest that we also have to bring this dimensions in a relation to the used wavelengths. This is very, very important. For instance, in the case of propeller-driven aircraft and helicopters, in brackets also of in case of drones, the motion of the blades can cause modulation effects of the radiated signal. This is visible on the receiver side. Then you can see this modulation depends on the turns of the propellers per minute. Examples of various types of avionic systems I have shown already on hand of this table. We have not discussed until now, but we have discussed the radio services here with different frequencies. And for instance, in case of wavelengths in frequency range below 2 MHz, this is on board of such an aircraft only for receiving equipment necessary or usable or applicable. Here in this table, I have listed again sorted after the frequencies. Low frequency means large wavelengths, sorted after, let's say, wavelengths, starting with the largest wavelengths, going down to the smallest wavelengths. All these radio services again. Here again for automatic direction finding. Then this frequency range, and here also the polarization is given. Long range communication, not only over satellite. In most cases, it's communicated via satellite, but you have other areas in the world. Then it's only they only can use this frequency bands. And then here, communication with the traffic control means you are in the near of the airport, starting and landing. Then we have here instrument landing system, also useful in the near of the airport. Then bearing instrument landing systems, also in case starting landing. Also this is useful in the near of the airport. Then we have here another frequency range. It's located over in the range higher than, let's say, the normal ultra shortwave radio communication system. It's for civil aviation exchange. Then this is used for military communication. Then also here, this frequency range, it was also already mentioned, is a so-called instrument landing system. It's active in the near of the airport, starting, landing. Then here, navigation, distance, and peering, also necessary in connection with the airport. Then this traffic control identification, it's also necessary if the airport comes in the near of if the aircraft comes in the near of the airport. Then here we have the navigation, for instance, GPS. This is navigation. There's nothing to do with the near of the airport. It has to do with normal flight route. Yeah, this is our measurement system for the height, the flight height, and here the weather radar, and all these very different wavelengths you have to handle on one aeroplane. Okay, this is here a new chapter, but it's connected with all what we have discussed until now. And I switch back to, let's say, to this radio service here, to automatic direction finding. Means the stations which this is a, let's say, a safety, a safety the system which works independent of the GPS. Maybe you are flying through some special zones with strong rain or such things. Then the GPS signal can be dropped down so that you have no control over your own position. And this very long wavelengths automatic direction finding system can help you also, let's say, keep on the self determination of your own position during the flight. And so it's not only nice to have, this is also a need. And so we need, for this very large wavelengths, I mentioned it's here roughly 200 meters, need special antennas to receive such very large wavelengths or low frequencies. And for this purpose, in the past, technicians, engineers developed the so-called loop antenna. And this loop antennas are used in these automatic direction finding systems. The polarization is vertical, and we will see what happens if we apply such a loop antenna. Such a loop, it's much smaller, or can realize much smaller than, let's say, a dipole, which works in let's say, half wavelengths or a little bit at smaller lengths. Regarding the wavelengths, we saw in one of the slides before a dipole with a length of 1% of the wavelengths. This also, we could apply this. The problem is, in such a short dipole, that the radiation resistance of such a wire antenna, of such a dipole antenna, it goes very, very fast to a very small value. Very small value means we have a lot of problems to use this signal coming out from such a dipole in connection with a receiver. If we have a low radiation resistance on the antenna side, and we have a, let's say, input resistance of our receiver, then we have a very large mismatch ratio. Means a lot of our signal, it's more or less attenuated by this large difference in radiation resistance and receiver input resistance. These two values should be more or less in the near, but should be not has a high difference. And this I mentioned already in one of the slides before, and now we come to overcome this problem, come to the so-called loop antennas. The loop itself has a different shape. It can be a circle, a square, triangle, whatever. It's clear that the circular loop antenna is one of the easiest to construct as well as to analyze systems. And so let's start with this loop antenna. It's a very small wire loop, high conductive material, let's say copper, for instance. But in theory, we at the first look, we use perfect electrical conductor, means the conductivity goes to infinity. So we have not to consider the effects of conductivity here in our theoretical approach. Yeah, how we can analyze it? the same method. In case of our dipole, we let's say that the starting point is the electric vector potential, and here in this case we use the magnetic vector potential. This is a formalism to applied to electromagnetic fields, and in this case the magnetic vector potential has this form here. It's similar to the electric vector potential. The rules are in principle the same, and here we can see that we're looking for a current element or current element. The current at the origin here, it's E0. It's also assumed in our case, because the loop is very small against the wavelengths, that the current distribution around this loop is also constant. This is like in case of the Hertz dipole. And so we look to a small current element with the length given by DL. You can see it here. This is the angle dphi, and the radius is the small r here, small a, the small a here. This is the radius of our loop, and it's clear that the length of this current element we want to observe is given by a multiplied by d phi. This or the q, it's the charge along this current element, but then we will see it later. And here the observation point, the distance of the observation point R from our current element, large R, to observation point P. These are the coordinates of the observation point, and you can see here that the R is given by the difference between this two this observation point, and this is the distance from the origin. Yes, and then we have only the difference between the single coordinates in square and the square root of this sum of this difference in squares here. This is again radius from, or distance from the origin, small r, and this is the distance from the current element, large R. Okay, now we apply the magnetic vector potential to this behavior, to the current elements. We also have to look for the product of this current element multiplied by the length. Again, current distribution around the circumference of this loop is constant, and so we can write it applying to the magnetic vector potential. We can write it in this way. Here we have the components in the x and y direction. This is the current at the origin. It's constant around the circumference, so it's not necessary to insert here an integral along the length. And now the magnetic vector potential A can be written in this way. We have to integrate around the circumference. This is the large C here. This is the integration around the circumference. And here we can write the two unit vectors in this way. This is only, let's say, the sum of all the components which are visible, or which we can see or can find here in spherical coordinates. So we can realize three individual components of this vector potential in spherical coordinate. It's clear. And the same like in case of our Hertzsche dipole in the radius direction, theta direction, and phi direction. And now we can also show that in the radius direction, the field components are negligible. I have written here 0. The same in the direction of the theta direction, because here we have the magnetic potential applied, and it's the opposite regarding the electrical field. And so we have only in the phi direction this expression, and this is comparable with that what we have achieved in case of the Hertzsche dipole. The only difference is that now in spherical coordinates the components are perpendicular to each other, and so we could find our E phi. In case of Hertzsche dipole, it's let's say 0, and here h theta. In case of Hertzsche dipole, it was also 0. Has this expression here, and now magnetic equivalent of Hertzsche dipole. Yeah, it's absolutely more or less comparable. Sorry, yeah, and this is shown that the E field is perpendicular, or the E field can determine in this way. This is our magnetic vector potential, and in case of H field here, again we have here the wave impedance. You know, the wave impedance is the main value which couples the magnitudes between the E field and the H field. The H field, in comparison with the E field, is by the wave impedance the magnitude smaller. All this is given here, and this is a cross product with also the means perpendicular to this field component to the magnetic potential as the cross product. And this leads to these two formulas. And this let's come to our last remarks. Again, why we use a loop antenna and not a short dipole antenna. Again, the short dipole also delivers us, let's say, a gain in the range larger than 1.8 dBi and a little bit smaller than 2.15 dBi. From this point of view, from the gain point of view, then I can say, okay, it's not a problem to apply a small wire for this frequency range of, let's say, 1 megahertz or 1.7 megahertz for this direction finding purposes. Yeah, again, if the dipole is much smaller than a half wavelength, then its radiation resistance drops down very dramatically. And so we can find here, in case of our loop antenna, what happens if we apply a loop, which, let's say, a diameter and a number of turns also much larger than a certain value. What we have discussed all the time for the theoretical approach, it's that the current distribution along the loop circumference, it's constant. In this case, it's not given. And all these formulas are developed in a direction of applying such loop antenna. Here you can see the radiation resistance, and consider my thought was we have to make the radiation resistance so large so that we have, let's say, more or less a good matching between this resistance at the feed point of our loop and the input resistance of a receiver system. in a lot of cases, the input resistance of a receiver system, it's about 50 ohm, only looking to the real part. Imaginary part should be small as possible, but it's not possible to make it zero, but very small. And now you can see what happens here. This is the formula regarding, for instance, the wavelengths dependence in n number of turns. It's given here, explained here, no. Large N, it's the number of turns, and A, it's the area of the loop given by the diameter of the loop. And what we have done here, we have multiplied this factor with, we have not multiplied, we have calculated out all these values here, and then we come to this 177. This factor, this is this, divided by the square of the wavelengths, number of turns, and the area of our loop. And now this is my example. If the area of the loop is given by 1% of the wavelengths in square, it's clear that's the area of the loop, 1% of the wavelengths in square, and the number of turns is only 1, then we can already achieve a radiation resistance of about 3.1 ohm. This we can apply directly. It's not. It's let's say based on the assumption that we have a current distribution around the circumference of non-constant current, means goes also after a sine function. And now if we increase the number of turns to 4, because all you can see here it goes in with the square. If we increase it of the number of 4, the number of turns of our loop, then we can achieve radiation resistance of 50 ohm. And with this value, we have a perfect match to the input resistance of a receiver system. And then I have tried to realize in case of a wavelength of 5 up to 50 meter, that means that the frequency in this case is much higher than 2 megahertz. This is in the range of several megahertz. It's shortwave range, like using by radio amateurs, this frequency range. 10 meters, it's about 30 megahertz. 11 meters, 27 megahertz. It's again much higher, but in this case, the loop radius can be 0.1 wavelengths divided by square root of p. Okay, what does it mean? Zero. Let's discuss this example. If we have a wavelength, let's say 10 meters, that means this is 1 meter, because a 10 meter wavelength, it's 1 meter here, divided by the square root of p. That means that the loop radius, it's much more. It's a half a meter about, or 30 centimeter. So then we can realize a very small antenna which has sufficient radiation resistance, maybe in the near of 50 ohm. And this is only what I want to show. If we go up with the wavelengths, let's say in the range of 150 meter, means the frequency it's only a tenth of that what we have discussed here. And then we came in the near of the service system of this direction finding receiver, frequency of the direction finding receiver. Then we also can build a loop with a diameter, let's say, of 1 meter about, and for instance, only also with 3 or 4 turns, and we also can achieve a radiation resistance of about 50 ohm. Yeah, if you are interested in, you can try to one times in your spare time. So far you have spare time, you can try to calculate it for, let's say, for such a automatic direction finding system. Means the loop diameter, let's say for, as an example, 1 for the lowest frequency and the other loop for the highest frequency here. Yeah, then we'll see in which way the loop diameter and the number of turns should be, how large should be the difference. And to make it comparable, you can assume in this calculation example, you can assume that we want to have the same diameter of the loop. Yes, the only degree of freedom to consider the frequency or the wavelengths, 190 kilohertz up to 1750 megahertz. We only want to realize this with the number of turns to achieve our, let's say, radiation resistance in the near 50 ohm. You can achieve 40 or you can also have 60, doesn't matter, in a near 50 ohm. This is the target or this is the goal. Okay, try to calculate this. Then again, and this is my last remark in this lecture here. You see here the Hertzian dipole rotation diagram or the pattern. This is the toroid with the inner diameter of 0. Our dipole, it's located here in this direction along the z-axis, or here it's shown this direction of the E field. And then this is the rotation pattern around this dipole. And now, in case of a small loop, it's named dipole, a small loop antenna, we have the same, more or less the same radiation pattern, but the E field direction goes in this, this direction here, the E field, and here we have our H field. And in case of the dipole, the Hertzian dipole, the H field has this direction. Means if I turn this diagram perpendicular to this one, then the E field goes in the same direction. Means the E field goes in the direction of the wires of our loop. Here, in this direction, are the wires of the loop located. Yes, here. Okay, I switch back. Means along the wire of our loop, this is the direction of our E field. The E field is swinging or pendling in this plane here, and not in this plane. This is the H field. This is the E field. And so we have a principle for a small loop antenna and the Hertzian dipole, similar radiation diagrams. I say similar because it depends on the achievable gain, but from, let's say, from the figures point of view, from the shapes point of view, it's identical. Only the polarization is regarding the E field or the H field. Depends on the comparison of the components, or exactly, this is visible here, perpendicular to each other. So thank you for the attention. And for the next lesson, it should be comfortable for me and for us also. If there a delay is visible, then please try to write me an email. One of your students, or one of the students I think he has my email address. Otherwise, I can send it via Dr. Hartmann. Okay, thank you again, and have a nice evening.
Thank you very much.
Thank you very much.
Okay, okay.
Thank you.
Bye-bye.